Hello everyone, I welcome you to my class, my lecture on vibrations of module number 4 of dynamics of machines. Some of the terms what we have gone through, I wish you to recall them. I am not going through again, repeating them again. The vibration, to and fro motion, periodic motion, motion which repeats after a fixed interval of time, like that. Non-periodic motion, what is meant by cycle, and what is time period, frequency expressed in F and omega. So amplitude, what is meant by degree of freedom. Then the classification of vibrations. So at least some of these terms you need to know. What is meant by free vibrations? Vibrations which take place in the absence of external excitation, they are called as free vibrations. Forced vibrations, vibrations which take place in the presence of external excitation, they are called as forced vibrations. Then longitudinal vibrations, motion. In these vibrations, the motion is along the axis, the lateral, perpendicular to the axis, torsional, above the axis, like that. Some of these terms we frequently use, you need to know them. Then we went through what is called a simple harmonic motion, a motion whose acceleration is directly proportional to the displacement, and in any simple harmonic motion. So if I call this as x is the displacement, then it is normally expressed as a sine of omega t plus phi. So x is the displacement, a is the amplitude, omega is the frequency, and phi is called as the phase difference. What is the phase difference? Two simple harmonic motions of same frequency, okay, or in general, any simple harmonic motion can be represented as a vector. Okay, we call it as the rotating vector. And if I have two simple harmonic motions, say, and having the same frequency, then those two can be related, and which is leading, which is lagging behind, etc., by what is called as phase difference. What is phase difference? Phase difference is the angle between two vectors representing two simple harmonic motions of the same frequency, and that's what is the phase difference. And then what do we mean by components of vibration system? For the study of vibrations, we build a system. We model the actual machine like that, or any structure, and using that model we make a study of vibrations. For this making the model, we need various components, various parts, and we had identified what are the different parts, and we had identified as 4 parts. One is the stiffness, the spring, the other one is mass, the third one is the damping, and the fourth one is what is called as external excitation. These are the 4 components required to build any system. Then we have what is called as resonance. Resonance is a very important phenomena which need to be avoided. Okay, as I said, all our practical problems are forced vibrations. The forced vibrations are the ones which create a problem for us. So why? And every forced vibrations has what is called as external excitation. And any external excitation shall have what is called as frequency. So what is the frequency of the external excitation? Okay, you have something. And you have a system, you remove that external excitation and allow it to vibrate, then you have what is called as free vibrations. Then find out what is the frequency of those free vibrations, and that is called as natural frequency. So for any given system, you have something what is called as natural frequency, and if that is subjected to external excitation, you have something what is called as frequency of external excitation. If the frequency of external excitation is the same as natural frequency, then we have resonance. This is a situation. Okay, then what is the problem with resonance? Resonance, if you operate the system at resonance, then very soon the system will collapse and it will fail. If you continue to operate the system at resonance, then you will find the amplitudes of the vibrations continuously increase, and in no time it reaches very high. Theoretically it reaches infinite. Unfortunately, you will not see the infinite vibrations. Before that the system must have collapsed. So therefore we have to take care that the system is never operated in resonance, and that is the, keeping that in mind, so we should know what is the natural frequency of any system. And next our exercise of learning is going to be on that. So we take various systems, of course single degree of freedom systems. Then what we do, what is the natural frequency of that system? That is what we are going to study. So the next topic title I am giving it like this. So undamped, so that means the system what I have is not going to have damping. Damped and undamped. If you have damping, then it is called as damped. If you don't have the damping in the system, then we call it as undamped. Undamped. The vibrations are free vibrations. That means I am not going to have any external excitation. Therefore, those vibrations are free vibrations. Undamped free vibrations. And that too, I can have this for any system having 1 degree, 2 degree, 3 degree. But our study is of single degree of freedom systems. So our study is going to be that. So single degree of freedom systems, build it, and then it should not have damping. Then allow it to undergo free vibrations, and therefore, okay, and then find out what is called as the natural frequency of the system. That's what. So our aim ultimately is going to be what is, okay. So before I really tell you what we are going to study, let us build the system. So I said I have components of vibration system. I had listed four components. One is spring stiffness. The second one is mass. The third one is damping. In this case, it is not there because it is undamped system. And the fourth one is external excitation. That also is not there because we have free vibrations. We have only two components. One is mass and the other one is spring. Okay, so the system is called as spring mass system. Okay, spring mass system. Okay, since I have only two components, the system looks like this. Very simple. So I have a spring. So representing it something like this. The spring is being represented like this. Okay, right now I assume that little later I shall take that also into account. I assume that the spring is of negligible mass. The spring mass is negligible, and I extend it. Okay, let me. Okay, when I extend it, this is the axis. You should be under the impression that all the coils are one side of the axis in the earlier diagram. So now I have made, and this is what is the axis. And right now, as I said, the spring is not subjected to any force. Right now, it is not subjected to any force. So any helical spring which is not subjected to any force, and if we measure the length along the spring, length of a helical spring measured along the axis, under no load, when it is not subjected to any load, okay, that length is called as free length. This length of the spring is called as free length of a spring. Okay, this is the free length because it is not subjected to any force, and therefore there is no question of going any extension or compression. Okay, this is a helical spring. I refer it. Its stiffness, which is supposed to be a constant. So a helical spring has a constant stiffness. What is meant by stiffness? How much load is required to have unit deflection? So unit means it may be 1 millimeter. So if you want to have 1 millimeter deflection, how much force is required? That is called as stiffness. So it means instead of 1 millimeter, it may be 1 centimeter, it may be 1 meter, anything like that. So K. So what is the unit I shall go for it. Say this is Newton per millimeter or Newton per meter. Well, if it is in Newton per millimeter, you can convert it into Newton per meter also. No problem. Okay, if you have say 10 Newton per millimeter, you can easily convert it. Say 10 Newton as it is. So I don't want millimeter, I want meter. So 1 millimeter is how many meters? So you know that it is 10 raised to minus 3 meters. So therefore this is going to be 10. Make this 10 raised to 3 Newton per meter. Something like this. You can easily convert from one unit to another unit very easily. So when you are substituting numerical values, okay, the chances of that are very less in this topic. But if at all you come across, then you need to be very careful about the consistency of the units. So otherwise no problem. Okay, don't worry. So now I shall just call it as K is the stiffness whose unit is force unit divided by the displacement unit. Okay. So now what I do? I am going to attach a mass. The second component of this spring is one that I have been represented. I take a mass and I attach a mass. And this is mass. Okay, the moment I attach a mass, you know that this mass, this box like thing which is having mass, it has weight. And the weight has been applied. Weight is nothing but a force. The moment I attach this mass is not going to remain here. And when I apply force, this spring will undergo extension. Let me assume that the spring will come down. And let me show little exorbitant the deflection or expansion of the spring, and this is the new position of the mass, and this is what I call it as static deflection. Okay, this is static deflection of the spring. Static deflection of the spring, and I can easily calculate how much is this. Okay, this I shall call it as a delta S. And how much it is? This is equal to how much force you have applied. How much force? That force is equal to mg, the weight. And what is the stiffness of the spring? K. Mg divided by K is what is called as the stiffness of the spring. Okay. Now please remember the mass is not here. The mass is here. Okay. You don't have two masses, and therefore I make it dotted. The moment I attach the mass is not going to remain here, it will come down. This is the position. Okay, the spring is one end is fixed here and the other end of the spring is here. Though I have shown as if the spring, as if it is a straight line, don't think that this is a straight line. Here also the distance between the two coils is going to increase, and here in this portion also you have coils. And this is the position. Now, is the mass moving? Is the mass moving? I attach a mass and leave it, and gradually it comes and it stops here. So therefore, this position is what is called as this position now is the equilibrium position. The mass is in the equilibrium state or equilibrium position. The system, okay, the mass and spring together, they are in the equilibrium state. They are not at all moving. Okay. So now this is the system what I have built, and this is a single degree freedom system. Okay, one variable is sufficient to define the location of the system at any time. That is why this system is called as single degree freedom system. Okay, now this system, single degree freedom system is built, and this, now what you are going to do, what we are going to do, or so in this study what we are expected to do, as I said, we want to find out what is the frequency of vibrations. That means I need to induce vibrations in this. This is a system, equilibrium state, fine. Now there are so many ways of inducing the vibrations. One way is, what I do is, I pull this mass, hold it, okay, and bring it down something like this, say up to here. Okay, I am still having the force and pulling it, trying to pull it downwards. I have brought it up to here. Now I release the force. I pull this mass and bring it up to here and leave it. Then what happens? The spring will try to pull the mass back, and the mass will start moving upwards, and it will not stop at this equilibrium position, and it will continue to move and go up and up, say probably up to here, to certain value. Then it doesn't stop there. Then again it will start moving down and down and down. It will cross this equilibrium position and go to the other extreme position. and this will go on. Since our system is undamped system, and theoretically this kind of thing going up and down and up and down, this will continue forever. Why? How? So now when I pull this, say I hold this mass and then pulled it, that means I have applied some force and brought it up here. That means that force, along with force, there is also some displacement. So force multiplied by the displacement shall give you what is the work done, or how much is the energy that I have put into this system. I have pumped some amount of energy into the system. Whatever the force multiplied by the displacement, that is the energy I have pumped into the system. So because of that energy, that is changing its, say it is moving, it is making it to move from here to here like that. And is there any dissipation of energy? So since the system is undamped system, there is no loss of energy. And therefore, as we all know that energy neither can be created nor destroyed. It can be only converted from one form of energy into another form. So here, the energy may remain as kinetic energy or potential energy or combination, but there is no loss of energy. If there is any friction, then I say that there is a loss of energy. So here there is no damping, and hence the energy will remain that much, whatever I have pumped in, and therefore this will go on vibrating even if you come after 10 years and observe if you really have this kind of system. If the system is really undamped system, then even after you come at after 10 years, once I start the vibrations, it will go on making it. So these vibrations which are taking place, do you have any force when the vibrations are taking place? So maybe at the initiation, while starting the vibrations, you have applied a force. But once I release it, there is no force acting on it, and these vibrations are taking place. This motion is taking place, and in the absence of any external excitation, and therefore these vibrations are what? These vibrations are free vibrations. So undamped system, and now I have induced the vibrations. They are free vibrations, and the system is single degree freedom system, and this is the kind of system. Please remember, this is not the only single degree freedom system. I shall show you so many single degree freedom systems. All that fine. Then what is to be done here? What is to be done? So as I said, so these are the vibrations. I want to study the vibrations, and what is to be done? So here we are going to do two things. One is what is called as our ultimate aim is to find, as I said, to find omega n, the natural frequency of the system. What is the natural frequency of the system? That's what I want to find out. And in some methods, so I am going to do this by various methods. I shall show you, I shall tell you what are the different methods. And in the process, we may also write what is called as a differential equation. Differential equation of motion. So when it is moving now, it is occupying different positions, sometimes here, sometimes here, sometimes here, and sometimes here, sometimes here, like that. I want to write down the equation. So using that equation, I substitute time, and I should be able to get where it is. And that kind of equation is what is called as differential equation of motion. These two things, as I said, this is our ultimate aim to find out. Some methods directly find out this. Some methods which we are going to discuss, they will find out directly this. And some methods, they will do this, and then from that, just by observation, we are going to get this. So how we are going to do all that? There are four methods what we are supposed to follow. We can use any one of these four methods, and the first method is what is called as Newton's second law. Newton's second law. Using Newton's second law, I can write down. The second one is what is called as D'Alembert's principle. I can use what is called as D'Alembert's principle. The difference between the first one and the second one is only if you understand what you are doing, then only you will be able to understand. Otherwise, it appears that both of them are one and the same. Very, very, very thin line of difference between the two, but both of them are totally different. So I shall also tell you what is D'Alembert's principle and how I can use it for our analysis. Okay. Then the third one is what is called as the energy method. Okay. So here this method makes use of the law of conservation of energy, the one which I made few minutes back the statement. Okay, that we are going to use. That is energy method. And the fourth one. Okay, since it is mentioned in your syllabus, we shall go through it and we shall also understand, but very rarely we use it. We use any of these things most of the times, and for the sake of the completion of the syllabus, we shall also go through what is called as the Rayleigh's method. Rayleigh's method. This also we shall go through, and this will find out, the last one as I said, it will find out only the natural frequency straight away. Directly the natural frequency is going to be found out. Okay, so let us go one by one, but before I do that, I have some more preparatory work. Okay, you all know what is simple harmonic motion. Simple harmonic motion. Okay, so simple harmonic motion is a motion whose acceleration is directly proportional to the displacement. Okay, and it is written in terms of either sine or cosine function. So simple harmonic motion shall have sine or cosine. So any sine function you can easily convert it into cosine, or cosine you can easily convert it into sine, as you know. Okay, sine theta is equal to cos of 90 minus theta. Okay, so like that. So x I can write it as a sine of omega t plus phi. This is a very common characteristic. Okay, what is the meaning of this? This is a simple harmonic motion. So what is the meaning of this or this if I represent? Okay, so now this phi is called as the phase difference, and omega is called as the frequency, and a is called as the amplitude. Okay, let us understand what is the meaning of this. Okay, so if I have another, say, simple harmonic motion, let me call this as b sine of omega t. Okay, so since the frequency of this, both of them are one and the same, and therefore they can be represented as vectors, and also they can be compared. I can say that this simple harmonic motion leads to this simple harmonic motion by an angle phi. Okay, so as we know, represent, what is the phi? Phi is the angle between the two vectors which represent the two simple harmonic motions of the same frequency. Okay, how do I represent? Let me represent the first one. I want to represent this as a vector. Okay, if I represent it, you can choose, say, a starting point or just center. Then you draw a line, say a horizontal line, just this line. I call this as the reference. This means at t equal to 0, this is my starting point. Then I have a vector which is whose length is b, and it is moving at an angular velocity of omega. It is moving at an angular velocity of omega. So I have an angle what is called as omega t, and draw this. And say this length t is equal to b, and where is this now? This is at t equal to, not t equal to 0, t equal to t. So in a time 0, in t seconds, it covers an angle omega t, and this is the vector, and its projection on the vertical, that will give you what is called as y equal to b sine of omega t. Okay, now I want to represent the another one. This frequency also, this is also rotating at omega. and in t equal to 0 it is not here and it is making an angle already, omega into t is 0, this is 0, that means sin phi. So when this is vector at t equal to 0, also it has moved, or in other words, in a time t, so what is the angle? Omega t plus phi. Okay, you have what is called as, you measure the angle phi and draw a line, and this length, what is this length? This length is equal to a, and from here to here, what is the angle? This angle is omega t plus phi. So what is the angle between this vector and this vector? That angle is phi. That is the phase difference. What is phase difference? Phase difference is the angle. Angle between what? Angle between two vectors. Okay, so what are those two vectors? Those two vectors are representing two simple harmonic motions. So phi is the angle between the two vectors representing simple harmonic motions. Simple harmonic motions of the same frequency. That is very, very important. Okay, so now let me start. So I don't have to explain what is this. I hope you have understood. What A is the amplitude, omega is the frequency, and phi is the phase difference. So now I would like to differentiate it once with respect to time and call this as x dot. This is a velocity. This is equal to a sine of, no, okay, sorry, a is a constant. Differentiation of this is nothing but cos of omega t plus phi multiplied by, okay, this is one term, and differentiation of this omega t plus phi with respect to, that is nothing but omega, and I shall write it as a into omega into cos of omega t plus phi. So now I would like to differentiate it once again. X double dot is equal to, on the same lines, a to omega is constant, and cos of omega t plus phi, this is nothing but minus of sin omega t plus phi. Again, differentiation of this is 1 more omega. So this minus sign I shall take it outside, and omega also, this becomes minus a omega square sin of omega t plus phi. Okay, so this is equal to minus as it is, omega square as it is. I shall take it as a sin of omega t plus phi. A sin of omega t plus phi is what? That is equal to x. Then I shall take this to the left hand side and write it x double dot plus omega square into x is equal to 0. What is this? This is a differential equation. What is this? The meaning of this is d square x upon dt square, the first term, plus omega square into x is equal to 0. This is the equation. Both of them in simple way we write this. Okay, so this is what is called as differential equation. Okay, so normally you don't go through this way. So now this is the differential equation. What is the solution of this differential equation? We have started our analysis or discussion with this thing. What is the solution of this differential equation? The solution of this differential equation is this. And what is the frequency of this? The frequency of this is omega. So where is omega here? That is nothing but this. The square root of this term, is nothing but the frequency. And that frequency is the natural frequency when we apply for that. There also we are going to have a very similar equation, and that equation also shall have what is called as the frequency, and that frequency is called as natural frequency. Okay, so what is the frequency? What is the solution of this? The solution of this is a simple harmonic motion. What is the frequency of that? The square root of this omega square, that is nothing but omega, that is the frequency. Please do not forget this. Every time I am not going to do this. So I shall write down any equation. Okay, say y double dot plus something, okay, some constant into y is equal to 0. Come across this. Okay, y double dot plus cy equal to 0. This is a simple harmonic motion. Okay, what is the frequency of that simple harmonic motion? That omega is equal to square root of c. So this is how we are going to do it by applying this. So why we use these methods? To get this kind of equation. This is called as differential equation. We obtain the differential equation and then use that differential equation to write down what is the expression for natural frequency. Okay, so now we take break now. We shall take break, and in our next class we shall apply all these things and one by one, and then get what is the natural frequency of the various systems. I hope you understand. Yes, do well. All the best.